crash course. Today we want to talk about preprocessing. Preprocessing is an important step when we want to build a machine learning pipeline. The preprocessing step consists of three different steps. The first step is Outlier Removal. First we write this down and then we talk about each of them. The second step is Data Normalization. Just note that we exclude preprocessing step and feature selection or feature extraction step from the preprocessing. And handling missing data that we learned how to handle them in pandas. Okay, what is outlier? Outlier is defined as a point that lies very far from the of the corresponding random variable. Let's say your data, you have two class problem and your first class data is something like this and the second class is like this. So if you use linear SVM in here, you will end up with a nice classifier and the decision boundary will be here. But let's say you have an outlier like this. So this data belongs to this class, and for just linear SVM, it could ruin the performance of SVM because it could change the classifier to something like this. Okay, so outliers sometimes are very important to remove. So especially for example in least square methods, when you want to fit a line using least square method, outliers are very important because they change the cost function so much. So if you have some data like this, then your line will be probably something like this. But if you have a data in here, then the cost function, which is the distance between your line and your data, is so much. So this could change your line into something like this, which is not at all very good line. So there are different techniques to remove outliers and different methods to train our model to be robust to outliers, but currently we don't want to talk about them. But you could actually see and take a quick glance of different methods in Sklearn in outlier removal. As you could see, one way is to fit some elliptic envelope to the data and then consider some of the data which are very far from that ellipsoid as outliers. And so there are different methods. Okay, the second thing that we want to concentrate on that in this session is data normalization. Sometimes feature values lie within different dynamic range. Thus, features with large dynamic range could have larger impact on cost function, and this is not necessarily true with their significance in classification. Let's say your data maybe is something like this. So in here, your data in y-axis are from the origin, but so let's say this is the mean value. So the y component of mean value are far from the origin, but the mean value, the x component of that is not far from the origin, and this could cause to have large impact on the cost function and decrease your classifier performance. So we have different normalization techniques to normalize the data before training our algorithm on that. The first method is to, and probably the most common one, is to standardize data, or standardization, or sometimes it's called mean removal and variance scaling. So the idea behind this is to convert somehow the distribution of your data to a Gaussian distribution with adjusting mean and variance. So if you have something like this, then so each data in this distribution is a 2D vector. So your normalized data is equal to your data minus mean value of your training data divided by standard deviation of your data. So let's say this is I. Yeah. Okay, so if you apply this transformation on the data like this, you will end up with a nice circular shape around the origin, which we will see that actually lots of algorithms consider that the data are zero mean. So or when you use L1 regularization or L2 regularization, they consider that your data has zero mean and constant variance. Actually, similar variance in different directions. So as you could see in here, the variance in this direction is less than the variance in this direction. So by transforming the data, we could somehow make the importance of y-axis and x-axis equal. Okay. And so this is important for RBF kernel in SVM if you use SVM, and if you use RBF kernel, and for L1 if you want to use L1 and L2 regularization. The zero mean and variance in the same order are the assumption of using these methods. The second thing is, the second method for data normalization is scaling features to a certain range. So in this case, probably it is commonly we want to scale data between 0 and 1 or -1 and 1. This is an alternative scaling algorithm. So we call this min-max scaler. Min-max scaler, and the motivation behind this in comparison with standardization is that it has some robustness to the data that has very small standard deviation. So as you could see in here, if you have very little standard deviation, so let's say your data is something like this. So in this direction you have very small standard deviation, then this division could actually ruin your data, because you have very small number in your denominator. It is very common that in implementation of standardization, people add epsilon to prevent the zero division in here, but still it could create some trouble for the data after normalization. So min-max scaler has the advantage that it is more robust to the data that has very low variance in some direction or in some dimensions. So if you want to standardize your data or use min-max scaler into range 0 and 1, you could apply the transform of x minus min of x divided by max of x minus min. You could easily verify that if you have any data, then any data will fall between the interval from 0 to 1. So for your maximum data, this division will be 1. So actually it is a vector, so all of that is 1. And for your mean data, it will be 0. Okay, because it will be mean minus mean, so it will be the same. Okay, now so these are linear transformation. Also for data normalization we have nonlinear transformations. There are two types of nonlinear transformation that are very popular. The first one is quantile transformation, and the second one is power transformation. So in quantile transformation, we want to put all features into some desired distribution. So if the cumulative distribution of your data is f of x, then quantile transformation wants to apply g minus 1 f of x, in which g is your desired distribution. So after applying this g minus 1 to, or g inverse to the f of x, you will have your desired distribution approximately for discrete data. So, and in quantile transformation, we want to map some distribution to uniform distribution. And the advantage of this nonlinear transformation is that they are less influenced by outliers, so they are more robust to outliers. And in fact, in comparison with scaling methods. But the disadvantage is that they could actually distort the correlation between data and actually distort the distances between data. Sometimes we want to map the distribution to Gaussian distribution. In fact, it is very common that when we build a machine learning model, we assume that the data has Gaussian distribution. So it is very good if we have a transformation that is able to convert any distribution to some kind of Gaussian distribution. For this, we use power transformation to convert a distribution to Gaussian distribution. Okay, and another technique for data normalization is scaling individual samples to have unit norm. Let's say we have some data like this, x1, x1, 2, and x1. So each data has m features, and we have n data. So this is one. Sorry, so okay. So in this case, maybe we divided each component by the norm of the whole this vector to make them have unit norm. So if we apply the transformation like this, let's say we are working with Euclidean norm, x1 squared, x1, 2 squared, and so on to x1 n squared, and apply this on the all of this data, then you could easily see that the norm of your new data is 1. So this is sometimes useful when you work with some data. When you use text processing, for example, this could be useful. Okay, now let's see this kind of pre-processing in scalar and learn how to use them in scalar and Python. Okay, core. Now first we want to actually work on iris dataset. So first we import from scalearn, we want to import datasets. Then we load the iris dataset. Okay, and for this example, we just use the first two features of dataset. We will see that currently, because we want to plot the data and visualize them, we use just two features, but in the future we'll learn how to use some transformations like PCA to use dimension reduction to visualize the data. But for now we just use the first two features of the data, and so the y is equal to iris target, and we could see the targets in here. So we have three classes. Maybe it is good to visualize the data with matplotlib. So you should import matplotlib.pyplot as plt, then we could plot. So in here we want to plot different classes with different colors. So we should use conditional selection in here. So first we want to select the data in which we have the target values 0 and the first component of that is 0, which means that we want to plot the x-axis, and the y-axis is the second component of them. And for the 0 we want to have red color and they are discrete, so we use O in here. We have the same thing for first class and second class, but we want to use different colors, so we use like green and blue for the third class, and we use plt.show in here. Okay, as you could see in here, these are our data. Okay, now we want to let's say we want to test RBF, SVM, and see the impact of data normalization in here. So from scalearn metrics, we import accuracy score to determine the performance of the classifier, and also to divide our dataset into train and test, we from scalearn.model selection we import train test split. In this way we could divide our data to train and test part. Okay, so it is train test split. The first argument is the first and second is your data and target values, and we want to put 20% of the data for test, and we use random state equals to 0 for this. Okay, now we create our classifier. So we want to use RBF SVM, so we use svm.svc. So first we should import SVM. So for importing SVM we should use from scalearn we should import SVM. So in here we have SVM. Let's say the kernel is RBF and gamma is 0.7, and we want to feed this on training data and y of train in here. So as you could see in here, I want just to, at first we want to see how does the classifier perform on just unnormalized data. So I train the RBF in here, and then I want to use accuracy score to see the performance of my classifier. So first you should pass the ground truth labels, which is y test in here, to the function. The second one is your prediction labels. So in here, prediction labels, you can get them with rbf svc.predict on the test data, and yeah, that's it. Let's run that. So for RBF classifier, actually SVM with RBF kernel, we have 63% accuracy on the test data. Now let's say we want to comparison it with different other normalization methods. So we use a simple loop in here for NN standardization, min, max, and quantile. If n is equal to standardization, then we want to have a normalizer equal to, so we have not yet import preprocessing from scalearn. So first we should import preprocessing from scalearn. So from scalearn we import preprocessing. Okay. So in here we create preprocessing dot standard scalar, so it means that we want to standardize our data. Else if we have min max, we want to have normalizer that is min max scalar, and otherwise we want to have quantile transformer. Okay. Now we want to normalize our data, so we use actually a new variable xtrain normalized is equal to normalizer dot fit so when you use fit transform, it will both fit the normalizer on your data and transform the data with the normalizer. So let's say if you just use fit in here, then you cannot have this in here. So just your normalizer extract the mean or some so for example, if you use standard scalar, it just extract mean and standard deviation from your data, but it does not apply the transformation on your data. If you want to transform your data, you could use fit transform. It means that it both fit and transform your data with that normalizer. So in here we pass training data, and it is so important, so much important to know that you should also transform your test data with the normalizer that fits on the training data. So when you want to transform and normalize your test data, you should use the normalizer in here. So we shouldn't use fit, we just want to transform. In other words, we just want to use the existing normalizer that fitted on the training data in here. So we want to actually normalize test data. Then similar to that, we train our classifier with normalized data. Then we print the accuracy based on normalized test data. Okay, it is transform. Okay, as you could see in here, when we normalize our data, we have got higher accuracy in comparison with the plain classifier. So it is very good sometimes to use actually normalization for your data. So it is an important step for pre-processing your data. Actually, we will see that also it is very important in neural networks or in deep learning to normalize your data before feed your network with the data. So in general, one of the important steps before training your algorithm is pre-processing the data and normalize the data with suitable transformation. And maybe it is hard to know intuitively that what transformation is best suited for your work. Maybe you want to use actually something like k-fold cross-validation to extract the best normalizer, but commonly using min-max or a standardization is very common and enough probably for your task. So maybe it is better to now have the building block in your mind. So for building a machine learning model from zero, you should first get some raw data, probably from Kaggle or from real world camera or anything else, then you will have pre-processing step. So in here you should apply outlier removal, data normalization, and also handling missing data. We learned how to handle missing data with pandas. Then you train your model. So it is very important step. Actually, we have another step which is in here, which is feature selection. That we talk about it later, but maybe we have lots of dimensions that are not really suitable and just cause cares of dimensionality for our classifier. So it is better sometimes to transform somehow our data or compress them in a way that we have more efficient features. Okay, yeah, that's it. I hope that you enjoyed from this session. See you in the next session. Bye.